the second day. I hope each of you had a good night's sleep and has enjoyed the interaction that we've been able to have here at this symposium. Our preliminary lecture this morning is going to be given by Jens Rostrup-Nielsen, and Cal Bartholomew, who is the past chair of the symposium, will introduce our speaker this morning.
Thank you, Jerry, and good morning, everyone. At the 7th International Catalyst Deactivation Symposium held in Cancun in 1997, several members of our deactivation community were recognized for their long and lasting contributions to the field. Professors Alexis Bell, Bernard Demont, and Gilbert Vermont received Founders Awards for their long efforts to, well, first of all, to get these deactivation symposiums going and to organize the first 4 and the 6th symposium. Professors John Butt and Eugene Peterson received the first Maxted Award in recognition of their contributions to research and teaching in the area of catalyst deactivation. Now, the name of the Maxted Award was chosen to honor the memory of E.B. Maxted, who made pioneering contributions to the field of poisoning, and particularly some concepts of poisoning that include selectivity, susceptibility, toxicity, and shielding. Dr. Rostrup-Nielsen will tell us a little more about E.B. Maxted, his life and accomplishments. Now, the scientific committee of the 9th ISCD determined that they would like to honor yet another person for their significant and lasting contributions. And it's most appropriate that we honor Dr. Jens Rostrup-Nielsen. Jens Rostrup-Nielsen began his career at Halder Topsoe in 1965, and since 1986 he has been director of R&D and a member of the executive committee. He received his Master's of Science from the Technical University of Copenhagen and his Doctor of Science in 1975, where his thesis focused on steamer-forming catalysts. Now, Dr. Nielsen's doctoral work was just the beginning of many years of pioneering research in the area of steamer forming, in which he has defined almost every area or aspect of steamer forming catalysis, including kinetics, the mechanisms, catalyst design and characterization, process design, modeling, and of course, every aspect of catalyst deactivation, including poisoning by arsenic, sulfur, carbon deposition, and sintering. And all of this was in addition to his heavy responsibilities as an executive at Halder Topsoe. And this work has resulted in a number of landmark publications that include the very definitive book and monograph on steamer forming, and over 87 reviews, journal articles, and 19 patents. Now, he has also made substantial contributions to the cause of science through his service to professional societies and governments. For example, from 1987 to 1991, he served as Chief Science Policy Advisor for the Danish government, and from 1995 to 99, President of the daughter-in-laws, one grandchild, one sailboat, and one dog. We are delighted to be able to present the 2001 E.B. Maxted Award to you, gents. And Professor Jerry Spivey will make that presentation, after which Dr. Rostrup-Nielsen will present his award address.
Gents, on behalf of the 9th International Symposium on Catalyst Deactivation, yes, we'd like to present to you this plaque and award in recognition of your E.B. Maxted Award, which consists of a plaque and a $2,500 honorarium. Thank you.
Thank you very much. Thank you very much for the very nice words, Candy, and thank you for the award. I feel very honored. Of course, I'm very happy. I hope most of it is true. And I tell you, our granddaughter is a wonderful girl. Let me start saying a few words about Maxted. I happened to meet with Frank Stone at the Limerick conference, and Frank worked, as we all know, at the University of Bristol, and that was where Maxted had most of his professional career. Maxted, as you can see from his year of birth, started already before World War I. He got his education in Britain, but he took his PhD, if you had something at that time, with Franz Fischer, Trucks Fischer, in Berlin. He also got married to a German girl, and then moved to Britain, and got associated with the University of Bristol, but he never had a membership of the faculty, and he got no salary. He earned his daily life by consultancy and patents. He made some patents for the gas industry and so forth. Of course, we all know him from the famous article in Advances of Catalysis, Volume 3. And for me, it was in particular that he was correlating the deactivation effect from the amount of poison on the catalyst and not the amount in the gas phase. To many of us, that looks obvious, but I tell you, when I started doing studies in steam reforming, it was all related to the sulfur content of the naphtha and the feed. And I started out following Maxted by determining steam absorption of sulfur on nickel, and no data was available in literature at that time. So from the very beginning of my career, I felt inspired by Maxted. Maxted was a strange fellow. He was a tall guy. He smoked pipe close to his experiments with a lot of leaking hydrogen pipes. He made very simple experiments on a bench and never with any safety. I feel that he has deserved to have the name on this prize, and of course I feel honored, but I'm sure you will find other persons being at least or even more qualified to receive this award. Now let me see. Whispker is this is a video which worked yesterday, but okay, I go back. Should work. What's wrong? Somebody here who knows about this? But otherwise, we will skip the video. Whispker carbon, we know is the phenomenon. Yeah, you need to click. No, you need to click here, and then the video should start. I'm sorry, you missed the best part of my presentation. If there's somebody outside who can manage that, I would be very happy. Whispker carbon is formed in tubular it has a peculiar mechanism. You will see the nickel crystal at the top growing with a carbon fiber following it. You will see that this is a severe process because the nickel crystal will change shape during this process. The fiber is very strong, and therefore if it hits the pore wall, the catalyst pellet will break down. So therefore we should avoid the formation of a Whispker carbon. Can you find out how we have the video work? We ran yesterday, but that's one run. Which more or less is related to the same kind of chemistry as you have in the formation of Whispker carbon. Now, if we look a little more closely on the mechanism, you could say that what happens is that the hydrocarbon or CO will decompose on the surface of the nickel crystal. Carbon will dissolve in the nickel crystal. Nickel carbide will not be stable, but the conditions we work at, temperature is too high, and then the carbon nucleates on the other side of the nickel crystal. There were in the beginning discussions that you have temperature gradient as a driving force, but you have exactly the same mechanism whether you decompose methane or whether you decompose CO. If you use very reactive molecules like acetylene, olefins, then the that if you start taking away a little bit of sulfur, maybe you could create a site where you could still activate the methane sufficiently for reaction, but not having room enough for dissolution of the carbon into the liquid. And this, of course, has been used in the so-called sulfur-passivated reforming process. When we form carbon by decomposition of methane in these systems, we get a very strange carbon structure with a lot of fibers. Apparently, it's kind of surface nucleation of the carbon, and we call it octopus carbon because that was actually to Greece. Now, the important point, as I said, is not the rate at which we form carbon, but how we can eliminate carbon formation. And what I will refer to is the situation in steam reforming. It's a question of the balance of the hydrocarbon either reacting to the gas and we get what I call the equilibrated gas by the steam reforming, the water-gas shift reaction, or whether the methane will decompose into carbon. At equilibrium, you have this equilibrated gas. It could be a question of whether the methane divided by hydrogen square will allow you thermodynamically to form carbon. Now, when looking at this equilibrium, we have to take into consideration that on a real catalyst, we will form the Whispker carbon having a higher energy content than graphite, meaning that we will have lower equilibrium constants on the catalyst than on graphite. And this equilibrium constant is not influenced whether you put a little bit of copper at least into the liquid crystal. And with that knowledge, we can construct a carbon limit diagram. This diagram was originally designed to confuse people, so they would think that we were more clever than we are. It's very simple, because the carbon limits are simply a function of the atomic ratio of oxygen to carbon, hydrogen to carbon, total pressure. From that, you can calculate whether you can form carbon within a certain temperature range. And this is what this diagram is about. And you can make these axes just showing which H to C and O to C ratios you have if you have mixtures of only steam and methane and only methane and CO2. And then on the right-hand side of this curve, you have the potential for carbon formation in some temperature range. And what these two curves show, this is graphite and this is catalyst data. And then you simply can take a combination of CO2, steam and methane and go into the diagram and see where you have thermodynamically a potential for carbon. Now, this limit is not just a fixed limit for any catalyst. As I said, it's related to Whispker carbon having a higher energy than graphite. This would mean that if you use smaller nickel crystals, you get thinner carbon fibers and thereby a larger deviation from graphite thermodynamics. And for sure, that is what we see. And you can make this equation. It means that if you have, for a given set of conditions, you have different carbon limits depending on the nickel particle size of the catalyst. If you use graphite, the calculations will show you that you could get carbon at temperatures below, 770. But if you use a catalyst, then it's between 770 and 550. But then if you start decreasing the nickel particle size, then if you come below, say 300 angstrom particle size, you are out of the carbon forming area. In fact, this was practiced in a syngas plant in the Netherlands some 15-20 years ago. you're seeing here is what I call carbon limit B. That is that on the left-hand side here, we have affinity for carbon formation in the equilibrated gas, meaning the equilibrium mixture resulting from the steam forming reaction and the water gas shift. And you have the principle of equilibrated gas saying that if that mixture has a potential for carbon formation, then you will get carbon. On the other side, you can say we could have conditions where we have a gas, that the actual gas has no affinity for carbon formation, then of course it will not form carbon. In between, we have the gray zone. And you could also ask yourself, is this thermodynamic limit, is that a law of nature? No. And how can we pass that carbon limit B and then avoid carbon? I should say that when I wrote my book in 1975, I thought we had learned everything, we knew everything about carbon formation and so on. Then, of course, a few months after it was published, we made a few experiments showing that this limit. Here you see the results again, where we have run pilot tests and also pilot tests being used in industry, conditions used in industry. First, if you say with a local metal catalyst, we have been running here with a CO2 methane ratio of 0.7 and a steam methane ratio of 6.9, and we are deep into the carbon forming area. But on the ruthenium catalyst, we will not form the carbon in spite of it, because we have this slow formation rate, and therefore we eliminate. Also here we have run with the sulfur passivation and with more CO2 in the gas, CO2 methane 2, and steam to carbon ratio 0.7, and also that has been practiced in industry. So it's possible to run beyond these limits. If we go back and say, out here, if we take higher hydrocarbons, we will always have a situation where we have affinity in the actual gas. The decomposition of the higher hydrocarbons is irreversible, and therefore we always have the potential for carbon formation. So we cannot use these simple rules. And the rate of carbon formation will, in steam reforming conditions, will depend on the type of hydrocarbon, ethylene being the most severe. Now you say ethylene is not that often the feedstock. Yes, it is. If you have too high preheat temperatures, then you will crack your hydrocarbon preheater and have ethylene coming to the reform. If you study the induction periods, this simple equation for carbon formation, this was from normal hexane, you'll see how this induction period is of course increased when you increase the steam to carbon ratio, and also how it decreases drastically when you increase temperature. As a result of this, you can say that for a given temperature, there is a steam to hydrocarbon ratio below which you will get carbon, and this you can analyze in a diagram like this. Here you have the actual temperature profile, and here you have the critical steam carbon ratio, which is a function of the catalyst, and it increases with temperature, as I said. This is for catalyst A, which is promoted catalyst. We have an I catalyst and unpromoted catalyst B. And here you have the actual steam to carbon ratio. If you have a high activity, you will use up your hydrocarbon quickly, and the steam to hydrocarbon ratio will increase. If you have some kind of poisoning or low activity, then the actual ratio will go like that, and you will see in a certain temperature range, even on this catalyst, you will get carbon formation. If you have an unpromoted catalyst, you will get carbon formation. So this is the situation out here that you can't say that for higher hydrocarbons that you can be free of carbon. You have to determine the conditions where you reach the critical steam to carbon ratio. For methane, the situation is different. For methane, you could say, I would like to make a conservative design. I would like to have a situation where in no place in the reformer I will have an actual gas composition with affinity for carbon formation. And if you do that, you have to take into consideration that this is not a simple reactor temperature-wise. You have the strong heat input, meaning that you have very strong radial gradients temperature-wise, but because of the very high Reynolds numbers, you have no concentration, radial concentration gradient. And you need a so-called two-dimensional reactor model in order to analyze the risk for carbon formation, requiring that at no position in the reformer would you have affinity for carbon in the actual case. Here you have a situation, just look at the yellow curves. Here we have a low activity catalyst. We have the carbon limit temperature Tm, meaning that is the temperature above which the gas composition will, at that point in the reformer, will have affinity for the composition of methane into carbon. Now the radial temperature profile would be like this, and it means that in an area close to the tube wall, you have that the actual temperature is above the carbon limit temperature, and this would lead to carbon formation or the risk for carbon formation. That way you can analyze how close you can go to carbon limits. You can understand that this is not a thermodynamic calculation, it's a kinetic calculation, and that carbon limits are very much influenced on the state of the catalyst, the heat flux, and so forth. But that's another story. How can we improve this situation? How can we say that if we have potential for carbon formation in the actual gas, how can we then eliminate carbon formation? And the classical situation is, of course, when you have steam reforming at the higher hydrocarbons. It's well known that that steam plays an important role, and that you could have spillover of steam to the surface, the nickel, and alkali is a good promoter, and also active magnesium oxide. There have also been other oxides suggested in the literature. However, recently more and more emphasis has been put on understanding whether you can eliminate the complete dissociation of methane on the surface. As I said, we worked on that many years back using the absorption of sulfur on the nickel surface under controlled conditions. Could we have sites available not having sulfur, not allowing the full dissociation of methane, but allowing the reforming reaction going on? And this resulted in these data in TGA with different units of the axis, but you see that the rate of carbon formation depends strongly on the coverage of sulfur. You have a strong coverage compared to strong dependency compared to that of the reforming reaction. Here you have close to 6.5, and here you have close to 3. And this brings us for a minute back to Maxted, because it means that we can express the reforming reaction as the rate of the non-poison catalyst multiplied by 1 minus sulfur coverage to the third power. Here you see the data for non-poison data on the non-poison catalyst, and this brings us to the famous Marx-Nielsen equation. Now, similar effects we tried to achieve by adding copper to the catalyst, and you will see that the situation is much more complicated. Here you have the rate of methane decomposition with different copper contents. This is the pure nickel catalyst. If we add just a little bit of copper, we see that we have an enhancement of the carbon deposition. With higher copper contents, we have the decrease of carbon formation, and the very high copper contents, we also get the formation of the octopus carbon, as we saw with sulfur. But it's not possible to achieve the high, say, coverage of copper or nickel as we can with sulfur, because you have a plate with the bulk composition. It's a very complicated story, and therefore copper cannot be applied. Gold is not dissolved in bulk nickel, and therefore, as you have seen several publications from us, by promoting the catalyst with gold, you can strongly decrease the carbon formation. All this we have say a semi-quantitative understanding. But recent studies has led us to more quantification of these things. What has happened over recent years is that we know much more precisely what is going on the surfaces, and we can see that the steps on the surfaces play a large role, and in a way that's a revival of an old idea. And I will complete my lecture by telling a little bit about that. First, for instance, interaction of sulfur with nickel. We understand much better. These are studies from scanning tunneling microscopy, and you see how sulfur and salt oxygen interact. You get sulfur on the surface and steam out. And also the structure of the sulfur or nickel after that process is different if you had put sulfur directly on the surface. We know these things in much more detail than we did, say, 10 years ago. The same is true for the deposition of carbon on the surface. All of these observations have been supported by theoretical calculations by means of density function theory calculations, and recently we carried out calculations comparing the methane activation on the nickel 1.1 surface and on the step surface represented here by 2.1. So today we can really make a picture of the energies involved in the decomposition of methane. You will see that on the nickel 1.1, the CH is the most stable thing, but on the step surface, the energy required for dissociation of methane is much less, and the most stable species on the step surface would be the adsorbed carbon atom. This is supplemented by the next. I'm so unhappy that we can't see this video. Let us pray. See where it starts. Okay. This is a fantastic thing. Here you see the nickel crystal. Here you see the graphite planes. And what the video would have shown is how these graphite planes comes out like waves. But then we will come down here, and then over this corner we will see that the carbon atoms are not coming out, the planes are not coming out here. No, they come out from a dislocation at the surface. You see first time this year. I've shown it in many countries, less civilized than this. I have also shown it twice in this country, but it doesn't work in Kentucky. But what it tells us strongly is that the nucleation of carbon is associated with steps on the surface. And then another observation. We know that if we put alkali on a liquid catalyst, we get a promotional effect on carbon formation. But we have to pay a high price, and that is that the activity goes down. This is the result of CH4 and CD4 exchanging burners. And you will see that if we add alkali to the catalyst, we have an increase in the activation energy, but we also have an increase in the pre-exponential factor. This was a little bit of a mystery until we collected the picture, also seeing that the carbon came from the steps. It means that we have a low activation energy on these sites, but we do not have that many of those sites. If we block these sites, for instance by potassium, then let's say it has to be activated out here. We have many more sites, therefore a higher exponential factor, but we have a much higher energy of activation. So that added to the picture. And then, of course, some of us came with good old ideas of B5 size and artifacts. One thought, we are back in the 60s, and that we could measure these B5 size by means of nitrogen. These measurements were later heavily criticized, but the next generation of surface scientists, they say these measurements, they were okay. So you have to wait long enough, then your old ideas come back. And I made also back in the 70s this plot. This was the logarithm of the nitrogen capacity, number of catalysts, and that was the rate. And the correlation coefficient is there, but it looks like a drunk bomber pilot trying to hit a railroad. At least you can see which way he flew, but it's not that convincing. Now, if you repeat, I will drop that. If you repeat the plots and say, okay, we just look at nickel aluminum catalysts, I should have shown that they have different contents of alkali. They do not have exactly the same nickel surface area, but you see quite a good correlation. So, we can say that also for gold, not just like alkali, for gold, when we put a little bit of gold on the nickel surface, we just block these step sites. So there is a number of indications that we have reactions taking place on the open surfaces, on the normal sides, and on step sides. And you have a competition of whether you get the formation of the carbon atom on the step side, because it is this XC which is a bad guy, and this is, of course, with the interaction of the sulfur. We work on that. We have a paper hopefully being accepted describing these things in more detail. So finally, let me come to conclusions. I hope I have given you the impression that it has been worthwhile for many years to work on this phenomenon. That's a pleasure of being in catalysis for many years. There are problems you can't solve during the length of a PhD study. You still have to have the patience for decades to really come close to what the solutions are. On the other hand, a lot of things we have seen has been described in literature long ago, and when Davy in his famous paper in 1817 described
John, you have one?
Well, I was going to say, how stable is the gold system? Jens, how stable is the gold on your nickel?
Good question. I think we use the nickel gold system as a system to study effects. I don't believe that the nickel gold system is ready for commercial catalyst. Also, you have seen in literature that we have used gold on ruthenium to study catalytic effects. You need to be sure that the gold atoms will stay where they are. And also, when you add sulfur to such a system, you have very nice things going on. So, I will not eliminate or say it could be likely that you could develop a nickel gold commercial catalyst, but we don't sell that product today.
Jens, on the same note, what about the nickel sulfur system? Is the sulfur stable over long periods of time in the nickel?
Yes. You have then to correlate the surface coverage, which is essential for achieving this effect, and this is a sulfur coverage, say around 0.7 to 0.8, and you should maintain that coverage. And that coverage is maintained by having a certain content of sulfur in your feedstock. And it's between 1 and 10 ppm. This was practiced in the big preformer of Sterling Chemistry in Texas City for more than 10 years. I can't tell how they added the sulfur, but that was a very easy thing. But we have made tests what happens if you shut off the sulfur. And you can run for a day or more, because as we all know, it's very difficult to remove sulfur from a poison catalyst. So it takes a long time before the sulfur coverage will come below the critical, say, 0.7. So in practice, it's easy to maintain that critical coverage. Of course, the catalyst activity goes down as with 1 minus delta S to the third. There's no problem in a reformer. You have a huge surplus of activity in a tubular reformer. You could run it with 100 times as much gas. It's not the question of a catalyst. What happens is that the temperature will increase more rapidly than in a normal tubular reformer, and then you can run at the same, say, conversion per tube as you do normally. And in practice, there's no problem. Unfortunately, I could say that there are very few situations in the chemical industry where you need these high concentrations of CO you get from CO2 reformers. And also, in order to achieve this with a very low steam carbon ratios and still operating at pressure, you will not get the sufficient conversion of methane. So, unfortunately, I have been disappointed. There have not been that many situations where the spark process or CO2 reforming with noble metals is a severe or significant industrial interest.
On that, when you mentioned the coverage of
Yep.
0.8,
It's 0.8 of saturation,
okay.
and in the saturation layer you have 0.5 sulfur atom per nickel atom. You know that.
Yeah. But what I was going to say is that coverage, the saturation coverage, will vary with the exposed crystallite planes. And so if you have low, say high index planes, you might be able to get a coverage approaching.
That's correct.
Maybe a coverage of 0.8 or 1.
If you go into the detailed analysis, and one of my colleagues is doing that now, it's not a question of the sulfur coverage on the 111 surface, it's a question of the coverage of the steps.
Yes. Yeah.
So,
And we can no longer talk about a C 2x2 structure.
No.
Other questions? If not, let's thank James again. Thank you.
see how it grows with the fiber coming, and you have the nickel crystal here, and you'll also see how the nickel crystal will change shape. It becomes almost pear shape. So it's a very strong process. And when these fibers hit the pore wall, the catalyst will break down. This is in situ, well-defined methane-hydrogen ratio. Terry Baker made similar things years back, but I think the conditions here are much more well-controlled. And what we can do is to go to a much higher resolution in this microscope. And that is what the next video is about. And yes?
One question, quick
Yeah.
question, yes. Does this provide you with information on the rate of growth?
Yes, sure, because, oh, please don't start. Yes, because this is real time. So, in fact, you can relate the growth rate to what you see.
Oh, well then.
Here we have the nickel crystal now, and here you see the graphite layers coming, and you see they are